Good everyone. This is the book that entitled Philosophy of Physics, which is edited by my chosen philosopher, Jeremy Butterfield, and his co-editor, John Ehrman. So my research is on advances and challenges in quantum theory application. Let's proceed to the next slide. First and foremost, let us know first the background of quantum theory. So when you think of the words quantum theory, we might ask or we might wonder what is quantum theory? Actually, quantum theory is explains the nature and behavior of matter and energy on the atomic and subatomic level. So what it shows is that these entities behave at times as particles and at times as waves. So in particular, it is talks about the wave nature of electrons. So quantum theory tells us that physics is actually essentially indeterministic, so that particles may be somewhere without being at any particular place, that they may have energy and momentum without having any particular value for them, and it hosts more non-classical oddities. So most of these ideas are simply kind of unfamiliar conceptions, and in the end, the best thing is just to get used to the idea that the world depicted by quantum theory is very different from the world delivered by our senses. Um, the questions again come into my mind is that is quantum theory useful to us today, or it is relevant to us today? Yes, um, quantum mechanics makes it possible to design many modern electronic devices such as lasers, electron microscopes, magnetic resonance, imaging, or devices and the components used in computer hardware, not to mention the bread toaster at breakfast. So quantum physics is basically explain why hot objects glow red. So what is really the problem of measurement in quantum theory? So just like all other objects on the atomic and subatomic level, quantum objects, which is an electron behaves partly as a wave and partly as a particle. It is said to be quantized fluctuating probability wave functions. When you try to observe or measure this wave function, the device that we use will affect the wave function such that instead of fluctuating, it is transformed into a definite state with well-defined value that can be measured. So this transformation is called the wave function collapse. When this happens, the electron is no longer in its natural wave state and can be measured using classical techniques. So this is why quantum theory has problems of measurement and therefore of interpretation. So Jeremy Butterfield approaches this subject from a philosophical point of view in his article. So this is my supporting points. So the success of quantum theory and its application beyond the original one. So first, the supporting point is talks about original quantum theory was thought up for a system of atomic dimensions, 10 raised minus 8 centimeter, but it turned out to be unuseful both. So A for much smaller scales around 10 raised minus 12 centimeter, and also B for much larger systems, as in case of superconductivity and superfluidity, involving scales up to 10 raised minus 1 centimeter. The second supporting point would be quantum theory, which was meant to deal with the very small objects, was also found to be useful in astronomy, such that, for example, nuclear physics is able to develop a very accurate and detailed theory of stellar structure and evolution, including the creation of nuclei in stars. This is the third supporting point, which is quantum theory has also proven useful in physical cosmology. Now we know a lot about Big Bang, nucleosynthesis or primordial nucleosynthesis, the production of nuclei other than those of the lightest isotopy or hydrogen. So cosmologists believe that primordial nucleosynthesis took place in the interval from uh, roughly 10 seconds to 20 minutes after the Big Bang, and it's actually produced helium and lithium. However, we come to the objections. I think first objections would be um, another challenge of using quantum mechanics to describe uh, large system is that so-called quantum decoherence problem. According to quantum mechanics, the wave function of a system evolves in a deterministic way um, according to um, Schrodinger equation. However, when a system is interacting with its environment, it can become decoherent, which means that the wave function becomes irreversibly scrambled and system can no longer be described by quantum mechanics. So I think this is also a problem because it means that we cannot use quantum mechanics to describe the behavior of large microscopic systems that are interacting with their environment. And also, one of the principles governing quantum theory is actually unitarity demands a tight symmetry between past and future on a quantum level. So this presents a problems when we apply quantum theory to the universe. I think the main problem is that the universe is expanding. So this expansion is well described by general relativity, but it means that the future of the cosmos looks totally different from its past. The lithium problem or lithium discrepancy. This refers to the difference between the theoretical amount of lithium, which is based on the Big Bang nucleosynthesis or primordial nucleosynthesis, and the actual amount of lithium in the universe. So it should be estimated so that there should be three times the amount of lithium as we have now. Here are the possible answers to the objections that we had in the previous slide. The first, we might come up with the despite these challenges, researchers are continuing to work on developing new techniques and approaches that will allow us to better understand and describe kind of behavior of large quantum system. The secondly, it's we will answer to the objections of the second objections would be recently, quantum gravity theories may have found a way to loosen unitarity's backlash to better fit our growing cosmos, as Andrew Sommier and Jordan Kotler of Harvard University in their article they argued that a more relaxed principle called asymmetry can be accommodated in expanding universe while still satisfying the stringent so requirements that first made unitary a guiding light. And the last would be a solution beyond the existing standard model or standard cosmology might be needed. The standard model of particles physics is the theory describing three or the four known fundamental forces which electromagnetic weak and a strong interaction, excluding gravity. So in the universe and um, class elementary particles. Um, in conclusion, quantum theory started with atomic sized particles, but it's turned out to be useful for bigger system. Um, Notwithstanding some problems, especially in its relation to relativity, physics must continue to explore solution. I think that could be all, and thank you very much for attention.